Ireland, the land of saints and scholars. Ireland's literary heritage is well known, but in the history of mathematics too, Ireland has a role to play. For in the middle of the 19th century, discoveries were made that were to revolutionize algebra and lead to its final liberation from arithmetic. William Rowan Hamilton was born in Dublin in 1805. He was to become one of the truly great mathematicians of his time. From a very early age, he'd shown remarkable abilities. By the age of 7, he could read Greek and Latin and could recite texts of Homer in the original. At 13, he was able to perform phenomenal feats of mental arithmetic, such as calculating the prime factors of huge numbers in his head. His knowledge of advanced mathematics he acquired in his teens from the French textbooks used at the École Polytechnique. Works, for example, by Legendre and Lacroix. While still a student at Trinity College, Dublin, he was discovering original results in optics. He was elected Professor of Astronomy and Royal Astronomer of Ireland before he'd even completed his undergraduate studies. He was then still only 21. At about this time, one of his great achievements was his publication of the theory of systems of rays. It's a mathematical account of the behavior of light. Such a complex mathematical description of a physical situation had rarely been seen before in Ireland or elsewhere. And about 5 years later, he published his third supplement to his essay on the theory of systems of rays, in which he predicts how a ray of light will behave when it's passed through a prism with biaxial symmetry. We won't go here into what biaxial symmetry means precisely, but the important thing is that such prisms didn't actually exist, and so Hamilton had no experimental evidence to suggest what would happen. His mathematics predicted that a ray of light striking the prism at the correct angle would form a hollow cone inside the crystal and emerge as a hollow cylinder from the opposite face. This was called internal conical refraction. If, however, light was focused to a point on the surface of the crystal, it would pass through as a single ray and emerge as a hollow cone. Hamilton called this external conical refraction. Naturally, he was keen to see if his predictions could be verified. However, it took his colleague at Trinity College, Dublin, Humphrey Lloyd, some 2 months to obtain a suitable crystal and verify that the prediction for external conical refraction was indeed correct. As a result, in optics, conical refraction is a mere curiosity. But as an example of mathematical prediction, it's a tremendous achievement, one of the greatest achievements in mathematical physics. Its importance was recognized, and Hamilton was awarded the Royal Medal of the Royal Society in 1835. And a little later that same year, he was knighted at a meeting of the British Association held in Dublin. Thus, at the age of 29, he was recognized as one of the greatest applied mathematicians of his day. At that meeting of the British Association, Hamilton presented 3 papers under the heading Theory of Conjugate Functions or Algebraic Couples, with a preliminary and elementary essay on algebra as the science of pure time. Let's look now at some of the ideas expressed in these papers, beginning with the concept of algebraic couples. Hamilton, like many others, was interested in the formal algebra derived from complex numbers. A complex number has the form a plus bi, where I is an imaginary quantity which satisfies the rule I squared equals minus 1. Complex numbers can be added. For example, 3 plus 2i plus 4 minus 1i is 3 plus 4 plus 2i minus 1i. which is equal to 7 plus 1i. They can also be multiplied. 3 plus 2i times 4 minus 1i is equal to 3 times 4 plus 3 times minus 1i plus 2i times 4 plus 2i times minus 1i. And because I squared equals minus 1, this eventually becomes 14 plus 5i. But this imaginary number I was a source of some controversy at the time. However, Hamilton, following the methods of Wessel, interpreted complex numbers as points on a plane. So 3 plus 2i could be interpreted as the point 3, 2, using a pair of coordinate axes. What Hamilton did was to dispense with any concept of imaginary square roots of minus 1 and simply consider number pairs or couples. He defined rules for adding couples. AB plus CD equaled A plus C, B plus D. And for multiplication, AB times CD equaled AC minus BD, AD plus BC. In particular, 0, 1 times 0, 1 equaled minus 1, 0. This is in fact an exact parallel to addition and multiplication of complex numbers. Hamilton avoided talking of imaginary numbers by starting with number couples and defining a set of formal rules for their addition and multiplication. The logical development was to consider number triples, or triadic fancies, as Hamilton called them. In other words, to look at number triples like A, B, C, to find rules for their addition and multiplication, Hamilton tried to extend the analogy from complex numbers. He interpreted A, B, C as A plus BI plus CJ, where both I squared and J squared equaled minus 1. Adding triples was easy. For example, 3 plus 2i plus 4j plus 1 plus 4i minus 3j equals 3 plus 1 plus 2i plus 4i plus 4j minus 3j, which gives this. But the question now is, how do you multiply triples? Multiplying these two triples as if they were complex numbers produces this extra term in ij. What is this product ij? What can ij be? Hamilton pondered this question for a long time, so much so that it seemed to become something of a family joke, as he tells us in a letter to his son Archibald, written some years later.
Every morning on my coming down to breakfast, your little brother William Edwin and yourself used to ask me, "Well, Papa, can you multiply triples?" Whereto I was obliged to reply with a shake of the head, "No, I can only add and subtract them."
Hamilton tried several methods of attack over the years. Part of his problem related to what he called the modulus of a triple. For example, the modulus of A plus BI plus CJ is just the square root of A squared plus B squared plus C squared. And he wanted the modulus of the product to be equal to the product of the moduli of the individual terms. And none of his attempts for a value of ij allowed him to achieve this. And then suddenly, one day, it was the 16th of October, 1843, he had the necessary flash of inspiration.
As I was walking with Lady Hamilton to Dublin and came up to Broome Bridge, I then and there felt the galvanic circuit of thought close. And the sparks which fell from it were the fundamental equations exactly as I have used them ever since. I pulled out on the spot a pocketbook and made an entry on which I felt that it might be worth my while to expend the labor of at least 10 or 15 years to come. But then, it is fair to say that this was because I felt a problem to have been at that moment solved, an intellectual want relieved, which had haunted me for at least 15 years before.
So excited was Hamilton that he actually scratched his formulae on the stonework of Broome Bridge. here's what he saw in his flash of inspiration. Instead of triples, using I and j only, he added a third distinct imaginary number, which he called k, also satisfying the rule k squared equals -1. So he now had quadruples, a plus bi plus cj plus dk, or quaternions, as he called them. To multiply quaternions, we use I squared equals j squared equals k squared equals ijk equals -1, so that ij equals k, jk equals I, ki equals j. But ij doesn't equal ji. Ji equals -k, kj equals -I, and ik equals -j. A good way of remembering this is as a cycle. Going clockwise round the circle, ij equals k, ki equals j, jk equals I. But going counterclockwise, ik equals -j, ji equals -k, and kj equals -I. With multiplication expressed like this, Hamilton had produced a consistent algebraic system of quadruples, but one in which multiplication was not commutative. This was the first non-commutative algebra ever to be developed, and it's why we say that Hamilton freed algebra from arithmetic and opened a way for other mathematicians to re-examine the basic concepts of algebra. Hamilton was so pleased at the result that he wrote a poem in commemoration of it.
And how the one of time, of space the three, might in the chain of symbols girdled be.
Hamilton saw the four elements of a quaternion as expressing the three dimensions of space, the vectors I, j, and k, and a single numerical dimension of time, the scalar. By the following year, quaternions were beginning to be applied by Hamilton and others, and applications to astronomy were being published. But 1844 was also an important year in the life of a little-known English schoolmaster, George Boole. Boole was then 29 years old. He was running his own school in Lincoln. He had also just received the first Royal Medal of the Royal Society to be awarded for work in pure mathematics. Boole was born in Lincoln, the son of a local cobbler. Unlike Hamilton, he received no formal education and was largely self-taught. His mathematics, however, he'd also learnt from the French textbooks used at the École Polytechnique. Boole didn't have enough money to study at university, but that didn't prevent him from publishing mathematical papers, such as this one, the Notes on Quaternions, in which he shows a remarkable grasp of the subject. But a year earlier, he had published this work called The Mathematical Analysis of Logic. It's the first of two works for which he's chiefly remembered. And 7 years later, he wrote an investigation of the laws of thought, in which he clarifies and develops the earlier work in the mathematical analysis of logic. Of the laws of thought, Boole says,
I look upon it as the most valuable, if not the only valuable contribution that I have made or am likely to make to science, and the thing by which I would desire, if at all, to be remembered hereafter.
However, much had happened to Boole in the 7 years between the publication of these two works. In 1849, he was elected the first professor of mathematics at the newly founded Queen's College in Cork. And so he moved here to Cork, where he was to remain for the rest of his life. Indeed, we know that he lived in this house and wrote part of the laws of thought looking out over the River Lee. Boole states quite clearly the purpose of his book in the opening paragraph.
The design of the following treatise is to investigate the fundamental laws of those operations of the mind by which reasoning is performed. to give expression to them in the symbolical language of a calculus, and upon this foundation to establish the science of logic and construct its method.
He starts to set up his calculus of logic by saying,
Let us then agree to represent the class of individuals to which a particular name is applicable by a single letter, such as X. Thus, if an adjective such as white is employed, then let us represent by the letter X all white things. If we let the letter Y represent all sheep, then let XY stand for all white sheep. In like manner, if Z stands for horned things, then ZXY represents white horned sheep. Let us now consider the laws to which the symbols XY, etc. are subject. It is evident that XY equals YX, but also if X includes all things in Y, XY equals X. Hence, XX equals X, or X squared equals X, for all terms of X.
this is a strange formula for its time. X squared equals X for all X. But Boole went on to develop an algebraic system based on these principles. He introduced plus as a symbol for or, so if A represents men and B represents women, then A plus B means all things that are either men or women. However, this operation plus can only be applied to sets of things that have no common members. Notice that at this stage, Boole avoids the problem of adding overlapping sets. Boole thus established an algebraic system representing what we now call set theory. But he developed these ideas further. He says that if X represents all white things, then 1 minus X represents all things not white. Since objects can't be both white and not white at the same time, then X into 1 minus X equals 0. Or X minus X squared equals 0. So X squared equals X, as before. Yet how could any element multiplied by itself remain just the same? There are only two numbers in arithmetic, 0 and 1, for which this is true. All other numbers fail to satisfy this rule. Yet here was an algebra in which X squared equals X for every member X of the algebra. This was a clear break with arithmetic, but perhaps not all that surprising, since it didn't owe its origins to the idea of number. The British mathematician De Morgan said of this work,
He has, I think, got hold of the true connection of algebra and logic.
Boole's work led to further significant departures in conventional thinking in algebra. De Morgan, following up Boole's ideas, pointed out an interesting variation of the distributive law in Boole's algebra. With an eye to future applications of Boolean algebra, we'll demonstrate this using electric circuits. We can represent the formula A times B plus C by a circuit with a switch A in series with a pair of switches B and C in parallel. So times means in series and plus means in parallel. This arrangement of switches is equivalent to putting A and B in series and then these two in parallel with a copy of A and C in series. To allow current to flow, we can either switch A and B or A and C. This second arrangement expresses A times B plus A times C. This is the normal distributive law we know from arithmetic. But now consider A plus B times C. This is switch A in parallel with B and C in series. But this is the same as A and B in parallel put in series with a copy of A and C in parallel. Current flows if we operate either A by itself or B and C together. The expression for this second circuit is A plus B times A plus C. This is a second distributive law, an exact match for the first, but with plus and times interchange. However, as far as arithmetic is concerned, this second distributive law is nonsense. Thus, we have yet a further example of how Boole's algebra led to conflict with the laws of arithmetic. The works of Boole and Hamilton were to revolutionize mathematics in many ways. De Morgan, in a letter to Hamilton, acknowledges this breakthrough.
All metaphysicians, except you and I, and Boole, consider mathematics as 4 books of Euclid, and algebra up to quadratic equations.
Although Hamilton himself failed to apply quaternions very extensively, and they were never really widely used in practical applications, they did inspire further developments in applied mathematics, particularly in quantum physics on one extreme and space-time on the other. Boolean algebra was taken up most effectively in 1938 by the American engineer Shannon. His paper, A Symbolic Analysis of Relay and Switching Circuits, based on Boole's analysis of logic, set up the logical basis on which modern digital computer circuits are designed. But aside from physical and practical applications, by freeing algebra from arithmetic, Boole and Hamilton did much to give algebra its present place in pure mathematics. There are many commemorations of Hamilton and Boole. The plaque on Broome Bridge, where Hamilton discovered quaternions, and these Irish postage stamps, including one reproducing the page from Hamilton's notebook. And here in University College, Cork, which is what Queen's College is now called, we have this magnificent stained glass window, a tribute to George Boole and to his place among the mathematicians, scientists, philosophers, astronomers, and other great scholars of the past. Bacon, Napier, and Newton, Aristotle and Euclid, Pascal, Leibniz, and Descartes, and above Boole in the center, Pythagoras. But there's one other place where you'll find Boole and Hamilton and most of the other great mathematicians of the past commemorated, and that's on the surface of the moon. Here, near the crater of Pythagoras, is a crater named after Boole. And almost diametrically opposite, we find a crater named after Hamilton. And indeed, here on the surface of the moon, you'll find features named after almost all of the mathematicians that you've met on this course.